All right, so one of the main applications of statistics is estimating population parameters from sample statistics. So in this lesson, we're going to learn how we can use sample data to estimate population parameters. There are really two types of parameter estimates. There's a point estimate, which would be a single number that best represents the parameter. We can think of like the mean, median to represent the center, the standard deviation to represent the spread. Or we can have an interval estimate, which is a range of numbers around a point estimate that we believe the population parameter is going to be in. And in statistics, we call this a confidence interval. So a confidence interval is simply a point estimate plus or minus some margin of error. You've probably heard the term margin of error before, especially in like political polling, you'll hear it a lot. So you might hear something like a poll of 500 likely Tennessee voters showed that 47% would vote for Trump and 40% are likely to vote for Clinton. This poll has a margin of error of plus or minus 3%. So the margin of error then can be used to calculate an interval around what we think the population parameter actually is. What this was saying is, so we are confident then that the proportion of likely Trump voters would be anywhere between 44% and 50%. We take that point estimate 47 and add 3 to it and subtract 3 to it. So that's an example of a confidence interval. Another example of a confidence interval you might see on the weather. You think of the little confidence bands that are around hurricane predictions. The line here, and here you could think of as the point estimate, and then the bands around it as the confidence interval. The meteorologists are, pretty confident that the hurricane is going to fall somewhere within this cone of uncertainty. It's going to fall somewhere within this interval. The two most common types of confidence intervals you might see in research would be the 95% confidence interval and the 99% confidence interval. And these relate back to the alpha level we discussed a little bit earlier. So it's called the 95% confidence interval because we're allowing a 5% chance that the parameter will fall outside of that range. It's the same thing. We're allowing a 5% chance of making a type 1 error, right? It's related to our idea of the alpha level. And so these are really based on, similar to the rules, the properties of the standard deviation and the normal distribution. Remember that around 95% of cases will fall within 2 standard deviations of the mean. So we will use these principles to help build our confidence intervals. One tricky thing is the interpretation of the confidence intervals. The thing we're confident about in a confidence interval is the sampling procedure. It's technically not accurate to say that there's a 95% chance or a 95% probability that the population parameter is within our confidence intervals. What we're actually our confidence is based on this idea of repeated sampling. If we were to repeatedly take samples from the population, calculate a mean, and calculate a confidence interval, and do that a large number of times, then 95% of those confidence intervals would contain the population mean, and 5% would not. That's what this picture here is supposed to illustrate. So here's the population mean mu here. Okay, we take one sample, we calculate the mean, and calculate a confidence interval. That confidence interval happened to contain the population mean. We take another sample, calculate the mean and the confidence interval, and that sample contained the population mean. Same thing for sample 3 and 4. But then in sample 5, it did not. We took a sample from the population, calculated the mean and the confidence interval, and our confidence interval in this case didn't contain the sample mean. this is really what the idea of a confidence interval is telling us, is that if we were to go out and repeatedly sample from the population, calculate confidence intervals each time, then 95% of those intervals would contain the population mean, 5% would not. We also need to talk a little bit about the t-distribution. So the t-distribution is just like the normal distribution. It's a bell-shaped curve, you can see in this diagram, where most of the values are occurring in the center and fewer values are occurring at the tails. The difference between it and the normal distribution is the t-distribution has fatter tails. There's more occurring in the tails of the distribution. So we would say that it's more leptokurtic than the normal distribution. So the t-distribution was discovered actually by a chemist at Guinness Brewery in Dublin. William Gossett was interested in making inferences from small samples, who wanted to figure out about selecting the best types of barley to add to his beers. And he noticed that for small samples, the normal distribution did not do a good job of approximating the population parameters. So he actually developed the t-distribution for use in small sample cases. So sometimes you may hear this called like the student's t-distribution. The reason that is because Guinness had a policy against publishing trade secrets, so Gossett published under the pseudonym student here. So the t-distribution is a family of distributions. You see all these different distributions that are defined by what's called degrees of freedom. So each T with a different degree of freedom has a slightly different shape. It has to deal with how much is in the tails of the distribution. And the degrees of freedom are defined by the sample size minus 1 for the T distribution. So what are degrees of freedom? Degrees of freedom, the technical definition would be the number of values in a numerical array that are free to vary. And it may not make a lot of sense at first, so I have sort of this example here. So we have this equation, x plus y plus z equals 10. We can pick any value we want for x and any value we want for y. But in order for the sum of those three to equal 10, z would have to be fixed. So let's say, for example, we let x equal 2 and y equal 7. Then z in this case has to equal 1 in order for those three to sum up to equal 10. So in this case, we would say we have 2 degrees of freedom. 2 of these values, x and y, are free to vary. They can be anything they want, but z would have to remain fixed, in order for the sum to equal 10. So if we let x equal 4 and y equal 4, then z has to equal 2 in order for them to add up to equal 10. That's kind of an illustration of what we mean by degrees of freedom. It's the number of values that are allowed to vary so that you can get back to that fixed value, that mean, that sum that you're interested in. Another concept that'll come up is this idea of the standard error. So the standard error relates to what are called a sampling distribution. And it goes back to the idea of repeated sampling that I just mentioned. Let's imagine we took a random sample of 100 college freshmen. We gave them a test on statistical literacy and computed an average score. So the average score was 34.5. Let's say we did this again. We sampled 100 freshmen, gave them a test on statistical literacy, and computed their average score. We got 36.9. Let's say we did this again. We took a sample of 100 freshmen, gave them a test on statistical literacy, and computed an average score. Let's say we did this over and over and over again, a large number of times. Then we would have a distribution of sample means. So that's what this represents. This is our distribution of sample means here. And this is what's called a sampling distribution. These are really theoretical distributions. We don't go around calculating sampling distributions. But we have a powerful mathematical theorem that helps define the properties of these sampling distributions. And the central limit theorem tells us that the sampling distribution will approximate a normal distribution. So the sampling distribution of means, so a distribution of different sample means, according to the central limit theorem, will be normally distributed. The mean of that distribution of means would equal the population mean, and the standard deviation of that sampling distribution, which we call the standard error, is equal to the population standard deviation divided by the square root of the sample size. So in practice, we really only take one sample from the population, and we estimate the population parameters that we have, or we estimate the population parameters that we want from our sample statistics. So the standard error gives us that margin of error. You know, we can, the standard error is our estimate of the standard deviation of this theoretical sampling distribution. And remember, the central limit theorem tells us that the mean of that sampling distribution is going to be equal to the population mean, and that the standard deviation of that sampling distribution is going to be equal to the population standard deviation. The mean of the sampling distribution is going to be equal to the population standard deviation divided by the square root of the sample size. So let's talk a little bit about how we might calculate a confidence interval around the mean. So the general formula to do this is we just take the sample mean and we're going to add and subtract a margin of error. So we're going to add and subtract what's called a critical value times our standard error. So times our estimate of the variability in the sampling distribution, or the standard deviation of the sampling distribution. So the critical value is the value of the distribution that defines where the test statistic is unlikely to be. So if you think about the properties of a normal distribution, you know, where 95% of scores lie within 2 standard deviations of the mean, so anything occurring over 2 standard deviations might be considered unlikely. So that critical value helps determine like the limits on the confidence interval that we're interested in. So we want to know where it is in that distribution where 95% of the scores would lie. Like in the normal distribution, around 95% of scores are going to be within 2 standard deviations of the mean. It's really within 1.96 standard deviations of the mean. So to get these critical values, there's a nice online calculator here we can go to where we plug in the degrees of freedom, say what confidence level we want, say the degrees of freedom. We set our sample size is 100, the degrees of freedom will be 99, sample size minus 1. We want the 95% confidence interval. So this would be the critical value. So 95% of cases are within 1.984 standard deviations of the mean of a t distribution with 99 degrees of freedom. So that's what it's giving us there. So in this example, the mean reading comprehension score for a random sample of 25 sixth graders is 107 with a standard deviation of 15. We're going to calculate the 95% confidence interval for this mean. First thing we're going to do is determine the degrees of freedom. The degrees of freedom is the sample size minus 1. So the degree of freedom in this case would be 24. We need to look up a critical value here. So we'll go to our online calculator. So for 24 degrees of freedom, 95% of cases are going to be within 2.064 standard errors of the mean. So to calculate the standard error for this sampling distribution, remember the central limit theorem tells us that the standard deviation of the sampling distribution is going to be equal to the population standard deviation divided by the square root of the sample size. Well, since we don't know the population standard deviation, we're going to use the sample standard deviation to estimate it. Since we're estimating the population standard deviation, it adds a little bit of error into our measurement, and that's really the reason we're using the t-distribution as opposed to a normal distribution. So the t-distribution, it has fatter tails that takes into account this extra bit of uncertainty that we're introducing because we're using the sample standard deviation. If we knew the population standard deviation, we could actually use the normal curve instead of the t-distribution. We could use the normal distribution. But we typically don't know that, so we will estimate the population standard deviation with the sample standard deviation in order to calculate the standard error. And so that's why we're going to use the t-value and the t-distribution to calculate the confidence interval. So, and then basically once we have all these pieces, we plug into the formula. We have our sample mean, 107, plus or minus our critical value, we got it our calculator, times our standard error, which would be our sample standard deviation, 15, divided by the square root of the sample size, 25. So our confidence interval would be then we're 95% confidence that the population reading comprehension score would be between 101 and 113. Technically what this is saying is that if we repeatedly sampled sixth graders and computed confidence intervals, then 95% of those confidence intervals would contain the true mean reading comprehension score. That's what we're actually 95% confident about. Let's look at another example. So a marketing researcher for a major U.S. gene manufacturer would like to estimate the mean age of the population who buys its genes. This information could be very valuable for how to expend advertising dollars. For example, should we advertise in 17 magazine or should we advertise in Cosmopolitan? These publications have different, or aimed at different demographics. So, it would be too costly and too time consuming to record the age of every person in their population of customers. So we take a random sample of 30 customers and ask them their age. And we did this, the mean age for this sample was 30 and a half years, and we had a standard deviation of 24.45. The marketing researcher asked you to compute a 95% confidence interval for this mean. So instead of just using the sample mean, we want to create an interval around it to where we are confident the population mean might lie in. So first thing we do is we determine the degrees of freedom to use. So this is easy. It's just a sample size minus 1. We can then plug that in to find our critical value we need in our critical value calculator. Let's see. We had 29. We want the 95% confidence interval. Our critical value is 2.045. So for a t-distribution with 29 degrees of freedom, 95% of cases would lie within 2.045 standard deviations of the mean. Or since this is a sampling distribution, we'd call it standard errors of the mean. So then we just plug into our formula. Our sample mean plus or minus our critical value times our standard error. Remember the standard error, central limit theorem defines it as the population standard deviation divided by the square root of the sample size. We don't know the population standard deviation, so we're going to substitute the sample standard deviation, 24.45, and then divide it by the square root of our sample size. So if we do all those calculations, then we're 95% confident that the mean population age is between 21 and 40 years. So, given those results, maybe we want to advertise in Cosmopolitan instead of 17 magazine. So that's just a quick illustration and overview of calculating the confidence interval and how to interpret it. As always, if you have any questions, please email me or post to the message board. Thank you.